Hello, beautiful people. My name is Godwin. Welcome back to Economics YouTube channel. So, we've been talking about game theory in the last three classes. So, this is going to be our last class on this particular series for game theory. So, today we'll be talking about a subtopic which is extensive form games and backward induction. So, what is an extensive form game? It's not as if it's a new game, right? It's not as if it's a type of game. It's just a way of presenting your payoffs, the payoff of your um, players, right? After they've you know chosen the strategies to take, right? In a tree form. So when you put those payoffs in a tree form instead of in a matrix format, the one that we've been doing before. So now you are presenting your payoffs in a tree form. And in this particular instance, a player is definitely moving before another. So the ones we've been doing before this particular class have been simultaneous games, kind of, because not kind of they've been simultaneous games because it doesn't matter who moves first. So both of them are the two players or the players involved are actually moving, kind of any of them can move first, right? So that's what I'm trying to say. But in this particular game, one person has to move first. So you're going to say an example anyway. So an extensive form game is a representation of a game's payoff in a tree form, in which a player has to take a decision after the other player first took a decision, right? So you kind of have to wait. The first person has to take a decision, then that will determine the action, the line of action that you are also going to take. So, what is backward induction? Backward induction is the process of obtaining the subgame perfect Nash equilibrium of an extensive form game. Alright, so in this particular case, the method by which we go about obtaining our Nash equilibrium when we present our game in a tree form is what is referred to as backward induction. Okay, so we have an example. A thief wants the contents of a safe and is threatening the owner, and the owner is the only person who knows how to open the safe. So the thief is saying, I'll kill you if you don't open the safe, and I'll let you live if you do. So that's the threat. All right. With the value of each possible outcomes below. So these are the value of the possible outcomes. So question one says we should draw the game tree. Question two says what are the players' dominant strategies? And question C says, or the third one says, should the shop owner believe the threat and open the bag? Is the bag? It should be open the safe. And open the safe. So let us begin to dissect the question. All right. So we have the possible outcomes here. Open the safe. Thief does not. So T represents thief and S represents the shop owner. Open the safe. Thief does not kill. So the thief values that at 4 and the shop owner values that at 3. Not like 3 kg. Not like we have a unit of measurements. You understand? Just 4 and 3. Now the second is open the safe. Thief kills. So thief gets a value of 2. Then the shop owner gets a value of 1. Do not. So T stands for thief. The S is for the safe owner. So the if the owner opens the safe and the thief does not kill, the thief values that as 4, owner values at 3. Owner opens the safe and thief kills, the thief values that at 2, safe owner at 1. Owner do not open the safe and thief kills. So you can see the payoff there. And the last one, owner do not open the safe and thief doesn't kill. So here it is clear. Somebody is going first. It may look as if it's the thief, but the thief, whatever the thief is going to do, depends on what the safe owner does. So the safe owner is the one that is going first. So how do we arrange that? All right. So we have safe owner is the one going first. He has two strategies that he can use. So he may choose to open the safe and he may choose not to open. So it's either open or don't open. Right. So now we have the thief. So if the owner opens, the thief can do two things. The thief can choose to kill, and the thief can choose not to kill, don't kill. If the owner does not open the safe, the thief can still do two things as well. The thief can choose to kill, and the thief can choose not to kill. Right. So if the safe owner opens the safe and the thief kills, so where is that? The safe owner opens the safe here and the thief kills. The thief gets 2, the safe owner gets 1. Now, because the safe owner is the one playing first, so we are going to write the payoff of the safe owner first, right? So the safe owner gets open the safe. The safe owner gets 1. The safe owner gets 1, and the thief gets 2. Payoff of 2, right? So if the safe owner opens the safe and the thief does not kill, don't kill. The safe owner opens the safe and the thief does not kill. So the safe owner gets 3 and the thief gets 4. The safe owner gets 3, comma, and the thief gets 4. Okay. So if the safe owner does not open the safe and the thief kills, do not open and the thief kills, safe owner gets 2 and the thief gets 1. Safe owner is going to get 2, comma, and the thief will get 1. You can see that this stuff is easy. Okay. Now, if the safe owner does not open and the thief does not kill, safe owner, this is do not open and thief doesn't kill, safe owner, of course, will be able to keep his money. Okay, so 4. And the thief wouldn't like to commit murder in addition to robbery. So the thief gets 3. So safe owner gets 4. So we are writing the payoff of the safe owner first. So because the safe owner is the one that's going first here, so I should have used another color here so that this should have been blue. Should have been blue. So to make things 4, 2, 1, 3. Right, to make things kind of easy to follow. So this is the safe owner. 3, 1, 2, and 4. So how do we analyze this game? How do we get the dominant strategies? So how do we analyze this game? How do we get the dominant strategies? So the owner has 2 strategies, either to open or not open. So for the safe owner, so you can choose to open or not or don't open, right? So if he opens, the payoffs here, there are the 2 possible payoffs. If the safe owner decides to open, he can get either 1 or 3. Safe 3. Alright. If the safe owner decides not to open the safe, now this is where you have don't open. Now the safe owner is going to get 2 possible payoffs, which is depending on whatever the thief does. So if the safe owner is not opening, alright, he can either get the payoff of 2, or if the thief decides to kill, or gets the payoff of 4. So that's why you have 2 and 4. So if you look at it, 2 is better than 1, 4 is better than 3. Okay, so the safe owner's dominant strategy is not to open the safe. So that's why you have dominant strategy equals don't open the safe. How about the thief? Right, now the thief, the payoff of the thief is kind of not. Uh, there's a way you have to do it. Now you have kill here. You have kill here. So if the thief decides to kill, so the thief, if the thief kills, he can either get 2. If he kills, he can either get 1. So that's why if the thief decides to kill, he can either get the payoff of 2. If the thief decides to, this is kill, this is another kill, can either gets 2 or gets 1. Remember that the one in blue is the payoff for the thief, so 2 or 1. Now, if the thief does not kill, you have don't kill here, don't kill here. So you can either get 4 or get 3. Alright, so when you are making your comparisons, right, what should I even, um, don't mix them up. Now, if you're writing this as the first payoff for Q, so which is 2 here and 1 here. So when you have 2 and 1, so when you're comparing the payoff for don't Q, don't write this first before this. So don't write 3 and 4. That's not going to be correct. So don't write 3 and 4 here. So because you don't kill and kill this way, you picked this principal node first, kill here, and kill this way. So when you're writing the payoff for don't kill, that's will be don't kill, the one that is just opposite the one for Q, the first Q that you chose, and then don't Q for the other one. Do you understand? So if the safe owner decides not to open the safe, so don't Q here 4, don't Q here 3, so 4 against 3. 4 is better than 2, right? And 3 is better than 1. So you see that here, the uh, dominant strategy of the thief is not to kill, don't kill. So with that, we've been able to answer the question. So I've erased this because I wanted to write the assignment. So draw the game tree. We've drawn the game tree. It's not always this simple. There might be different designs, but anyway, it's still going to be a game tree. Still going to be in a tree format, right? So and that's one. So what are the players' dominant strategies? We just sort them out. So should the shop owner believe the threat and open the safe? So how do we answer that? That's to find the Nash equilibrium. Okay, but even before finding the Nash equilibrium, we know, or it's probably occurring to you that the shop owner should not open the safe. Why? Because this threat is not credible. So it's not a threat that the thief can carry out. Why? Because the dominant strategy of the thief is not to kill. So if the thief was saying that open the safe or I kill you, open the safe and I won't kill you. But if you don't open the safe, I kill you, right? So but now you consider his dominant strategy, no matter what the shop owner does, is not to kill. You understand? So like he is already engaged in armed robbery, probably, and he doesn't want to maybe add murder to to armed robbery. Okay. No, you can pass it, you can come. Good morning, it's happening here. So he doesn't want to add murder to armed robbery. So how do we get an equilibrium? Our Nash equilibrium is obviously going to be where their dominant strategies are intersecting. So it's going to be where the shop owner is not opening the safe, and when the where the what do you call it, the thief is not killing. So dominant strategy, sorry, Nash equilibrium is going to be don't open, don't kill. That's how I've circled it. Don't open, don't kill. So the payoff for the safe owner there is 4, and the payoff for the um there is 3. All right, so it's not difficult. Now it's not in all cases that you are going to be having a complete node like this, a complete tree. Sometimes your tree might be something like this. So maybe a company wants to enter a market, deciding whether to enter a market, but there are other companies in the market. They are going to react if this company enters, but if the company does not enter, they don't do anything anyway. So if this will enter and don't enter, so when it enters, the other companies are going to react, but if it chooses not to enter, nobody's going to do anything. So you might have a game like in this format. It depends on the question that you are dealing with. If you have any question, please leave them in the comment section. And if you are still running our school by then, so obviously students know where to submit the assignments, where they evaluate them and tell them if they are correct or not. So we have an assignment here. So it's you're likely going to think a little bit. It's not that straightforward. It's a little bit tricky, but you are good to go. Now, an allocator gets 200,000 naira from an experiment. So it's like someone is doing an experiment. So you have an allocator and then you have a receiver. So an allocator gets 200,000 naira from an experimenter and can divide the money equally between herself. So the allocator is a she now, a female. So between herself and the receiver, or share the money in the ratio 19:1, giving the lesser share to the receiver. So the allocator is taking the higher ratio and the receiver is taking the lower ratio. So if the receiver rejects the proposal, if the receiver rejects the proposal, the money returns to the experimenter. So, what is your prediction on how this situation is will likely turn out? So, what is your prediction on how this situation will likely turn out? So, what is this question asking you to do? And again, I didn't have that, but in addition to that, not really in addition to that, so I want you to present your answers in the form of a game, right? So, in the form of a tree. So that's what I mean. So you present your solution in an extensive fun game and then tell us what you think would likely be the turnout of this particular situation. So with that, we've successfully come to the end of our series on game theory. Like I said, this is the first class on game theory and Nash equilibrium of this particular series. So except something else comes up in the future, I don't think we might maybe return to game theory again. So until then, bye.